Morning.
Good morning. All right, so get started here in a moment. Oh, happy Monday. Oh. All right. So, okay. On Friday, we ended off talking about these things called inverse functions. We had been discussing compositions of functions, which look like this. F of g of x. And we found that there are some certain cases where f of g of x will give you back x. So if this is the case, then f of x and g of x are inverses. And this is essentially what it means to be an inverse function. This is something that I've kind of been peppering into the conversation all semester. When I talk about every operation has a, we'll say, an evil twin almost. The example we used last time was addition and subtraction. If f of x equals x plus 5, the inverse of that operation is g of x is minus 5. And same thing goes with pretty much every operation we have. Addition and subtraction, multiplication and division. Everybody kind of has their own inverse. But it also goes both ways. So addition is the inverse of subtraction, and subtraction is the inverse of addition. So the question that we ended off with last time is, how do we figure out what an inverse of a function is? And we have kind of hinted at it before. Does anybody have an idea of what we use to find an inverse?
Would you set it equal to something, or no? Would you?
I'm sorry, I couldn't hear what you said.
I said set it equal to something, but I don't think that's right.
Well, I mean, we'll definitely set it equal to something. So what that something is what we're going to try and think about. The whole idea of a function is it takes an input. Usually we just write x as the input, and it does a bunch of stuff to it and gives you something at the end. So very simple version of it is f of x equals x plus 5. Input is x, and the thing you get out is x plus 5. So an inverse of a function takes the thing you got out and gives you back the thing you started with. So if f of x gives you some output y, then the inverse of f, we denote that by putting that letter to a -1. If you take the output and use it as your starting point, your input, it will give you back x. And this is how we define, or we find an inverse, is we just take the original function and we switch the input and the output, and then we resolve it. Okay, so this is what we did when we were talking about transformations. What transformation does this correspond to? When we talked about translations, or I'm sorry, transformations, not translation, there was a certain kind of transformation that made us switch the input and the output, the y and the x. What was that?
Y.
So this was a reflection over the y equals x axis. So if you had your thing, and if you wanted to do a reflection over a line that went like that, the way we did that is we took y and switched it with x. So let's do some quick little practice with them. If our equation is, or I'm sorry, our function is x plus 5. We said the way that we find the inverse is we switch x and y, and then we resolve for y. So the first thing we do is switch those two, and you get x equals y plus 5. So solve that equation for y. What does y equal?
-3.
I'm sorry?
-3. Wait. Why?
It won't be a single number. If x equals y plus 5, what does y equal?
Sorry. Wait, say what you was going to say?
If x equals y plus 5, what does y equal?
X minus 5?
X minus 5. Yeah. So, and this is what we saw, what I said on the previous page, is that the inverse of x plus 5 is x minus 5. Here we have kind of proof for that. So this is the same. This is the same thing on all levels. So let's do another one. Y equals 4x minus 3. So everywhere we put, everywhere we have an x, we put a y. Everywhere we have a y, we put an x. So this becomes x equals 4y minus 3. So what does y equal?
Negative, 3x over 4.
Not quite.
Let me see. Let me look at it.
So we're trying to get y by itself. And when you're moving stuff to the other side, generally you follow the opposite order of operations.
X plus 3 over 4?
Yes. So we add 3, and then we divide everything by 4. So x plus 3 over 4. So this is the idea behind the inverse of a function. Take a function and you switch the y and the x, and then you have to resolve for y. So let's do one a little bit. How about so we switch them, we get x equals y squared minus 4. So what does y equal?
The square root of x plus 4?
I'm sorry?
The square root of x plus 4?
Yeah, so you take the 4 and you add it over. You have y squared equals x plus 4. So you have the square root of x plus 4. Okay, so we're going to look at this one for a second. And it's helpful to look at the graph. So y equals x squared plus 4 is a parabola. I'm sorry, x squared minus 4 is a parabola with a y-intercept of -4 and an x-intercept of 2 and -2. So it'll look something like this. All right. So now let's plot square root of x plus 4. What does the square root of x look like?
I don't know.
So let's plot it real quick. Let's do a couple quick points. When x equals 0, what does y equal?
0.
0. When x equals 4, what does y equal?
2.
What?
2.
2. So 4. What about when x equals 1?
1.
And then if you keep going, 9 and 3, but you get something that looks like that. Okay?
Mm-hmm.
But let's look at our transformations. There's a certain kind of transformation that makes us go from x to x plus 4. What kind of transformation is this?
It's a specific name.
I mean, not there's probably a very specific name for it, but let's think about the category. Is it a mirror or a flip? Is it a stretch or squish? Or is it a shift where we're just moving it around?
A shift.
It's a shift, yep. And the X means it's a shift which way? Left to right or up and down?
Left and right.
Left to right, okay. And now we're adding 4.
Going up. I mean, going right. I mean.
Remember, it's the opposite. So that's the weird part. Yeah.
Going left.
Yeah. So if it's adding 4, you go to the left. So the square root of x plus 4 is the square root of x graph moved 4 to the left. So something like that. Okay. And this is how the transformations thing helps, because it allows you to graph stuff that you may not normally be able to graph very easily. You can take a parent function, which is easy to remember, and then you can transform it into something new, which allows you to graph it. Okay. So does this green thing look like this blue one?
No. Yes. No.
Why yes and why no?
It's half of it, and then no, because it's going in a different direction.
Yeah. So it's not the same. Very, very good answer. It's not the same because it's only half of it. But it is the same because it looks exactly like the other half. And this is what we mean by an inverse is a flip over the y equals x line. So we have a y equals x line. This piece, if you flipped it around that, would actually look just like this side. But it doesn't have the other side, which is something like, actually we go through right there. Okay. So, sorry, my knees are giving out today. So this is kind of weird, not very great, that some functions don't really have a inverse function. The issue is when you did this part, y equals the square root of x plus 4. When you take the square root of something, what else are you supposed to do?
Oh, the plus and the minus.
Exactly. Very good. You're on fire today. Yeah, so you're supposed to do a plus minus. But if you have a plus minus, y equals plus minus something, then it's not a function anymore because it doesn't pass the vertical line test. So the vertical line test, for those who don't remember, is you take a vertical line and you put it anywhere on the function. And in order for it to be a function, it can't cross that graph in 2 or more places. So the original blue one was fine. Everywhere you put the line, it only went through it once. But the green one goes through that line twice. So that's why only half of it can be a function, is if you put the entire thing, then it's not actually a function. So this is a great showing of that. But there's something else about this graph that I want us to notice that is specific to these inverses. Is there anything that pops out? And I'll draw, I guess, what it theoretically would look like if you have the whole thing. Is there anything interesting, or there's something interesting to me about this blue graph, and when you flip it over the y equals x line, that dotted line, you get this green graph. Is there anything interesting kind of about that?
It looks like it got turned 90 degrees.
I'm sorry?
It looks like it got turned 90 degrees.
Okay, that's a thought, where it got turned, it looks like it got turned 90 degrees. And that's pretty accurate because this thing is 45 degrees from here. And so on the other side, it should also be 45 degrees from there. And so if you add those two together, it'll be 90 degrees. So that's an interesting take. I don't think I've heard that one before. So it reminds me of I don't even remember where I read it. I think it was one of those random shower thoughts posts. You can kiss yourself in the mirror, but only on the lips. I know, kind of deep for Monday morning, but in a mirror, could you possibly kiss your reflection anywhere except on the lips? Why not?
So it's a mirror reflection.
Yeah, like, so you couldn't kiss your reflection's hand, right?
Because it moves with you.
Because it moves with you. And in order to kiss your reflection, what do your lips have to do? Your lips have to touch it. But the only place your lips can touch your reflection is on the lips. Because if you put your hand in front of it, then your reflection is just kissing their hand like you are. Same thing with anything else. You could give yourself a high five in the mirror, but you can't give yourself a pat on the back because you could only touch the same body part. So similarly over here, look at where the two graphs touch the mirror. Right there. And right there. So that point, or both of those points, are the exact same point for each of the two mirrors. This one is at, I guess it's, what would have to be the point? So what would have to be the value of these 2 points? How would you find them?
What do you mean the value? Like,
so there's something we know about these 2 points. What else is true about this point, other than it's where this function meets this function? What line is it on? What is the equation of that dashed line?
is that y equals x squared?
Yeah. So if it's on the line y equals x, then what do you know about those points?
They equal each other?
That y equals x at those points. So at that point, this is true and this is true. So that means you have an equation. X equals square root of x plus 4, or x squared minus x minus 4 equals 0. So if you plug this in, you find the value of x, which is going to be throw out my calculator because we're running out of time.
X minus 4. No, x plus 4x minus 9.
So in this one, it's x equals 1/2 plus or minus square root of 17 over 4. So it's a weird number, and that's fine. But the point is, where 2 inverses, where they touch will always be along this y equals x axis. That's always where one of their intersections will be. I'm sorry, in this case, there's 2 intersections. 2 intersections on this axis. But one is at, you can't see that. So that's the number. Sorry, I wrote it too low. But one of them is at 1/2 minus that number, and the other one is at 1/2 plus that number. But they're both at along that line of y equals x. So you can find where they flip, and it's always along this line. So graphically, continue continuing along this idea, if you wanted to go point by point and flip them, it's actually even simpler than doing these solutions. So let's look at graphically flipping them. We said that 1, 2, 3. The blue one crosses there, there, there. So it looks something like this. So algebraically, how did we find the inverse? What did we do?
Change all the x's to y's and y's to x's.
Exactly. Very good. So if we have all of the points, what is the, I'll give you the point for this one. It's 0, -4. What about for that one?
0, 2.
It's not 0, 2.
2.
What?
2.
2.
0, negative.
So it's 2, 0. Because it's the x and then the y. And then this one was what? I think you said it, Delvin?
0, -1.
So x comes
0,
first.
-2.
-2,
Bro, why keep saying that?
0. So it's the x and then the y. All right, so we've got our points. Well, let's do the same thing that we did with the equation to these points. Let's switch the x's and the y's. Well, if you switch these two, it's -4, 0. -4, 0 is 4 to the left. Let's switch this one. 2, 0 becomes 0, 2. -2, 0 becomes 0, again, this is much easier on my, my smart board, so I apologize for that. But if you graph this, you get something that looks like that. So when you take the inverse of a function, if you're doing it graphically with the points themselves, you just switch all of the x and y values. So 0, -4 becomes -4, 0. 2, 0 becomes 0, 2. -2, 0 becomes 0, -2. If you're doing it algebraically, then the thing that switches is the y and the x in the map. And then you resolve it for y. So this is